Hello everyone, and today in this video I will talk about the Pyro-Solver, and also I will talk about turbulence, wind, temperature, advection, and I will also talk about density. Density we have covered, but in this video we need the density part. This video is important because in the upcoming videos, and we will cover the pyros, we will cover the smoke simulations more, like how do we create those real looking effects. Then we need the basics to understand. So this is like an overview of the Pyro-Solver, and we will create a simple setup, a simple smoke simulation, and I will cover the very basics. For example, turbulence, because turbulence is really important if you want to like have the real smoke like simulation like effect. So without wasting any further, let's jump into our video. And here you see I have the test geometry, and I've also created some notes. So this is just a simple note about Pyro-Solver, and you see I have a test geometry big head here. Let's create a sphere also, primitive, and I want to create our fog volume VD from particles, because this sphere is a primitive sphere, so we need particles. I have covered this primitive sphere in detail in the cloud video. So if you want to like know about this primitive sphere, you can watch that. And we have the test geometry here, VDB from polygons. Sorry, VBD from polygons. Connect this, and you would see something like this. I don't want distance, I want density, and here I want density, but here I want to say temperature. And I like want to tell you really something important thing here. I will create a note. When you are saying density, those values that present in these voxels are now referred to as density values, are referred to as volume density, volume attribute density. And when I'm saying I want these same values but as temperature, so now these values are stored as temperature. Values are same, but they are like stored in different, they are like called different field values. For example, this is volumetric attribute, but this is density, and here these values are temperature values. So density values, but values of attribute, volumetric attribute density, and here the temperature is values of volumetric attribute temperature, right? This is the real difference. These are values, and we are calling these values like different with different names. So Houdini, when Houdini try to recover those values, will try to read those values, so it would read these values differently. Same values are coming from density, same values are coming from temperature. Temperature have different effects, but density have different effects. I will explain how. So now we have different types of, like we have different VDBs, right? We have this from particle, and this is our temperature values, and these are like our density values. Let's merge them. Not merge them now. Let's create our Pyro-Solver. So what this Pyro-Solver do? This Pyro-Solver tells how density values or temperature values will have the effect on the data these voxels have. What do I mean by that? Pyro-Solvers will tell Houdini how these values evolve over time or change over time. Right? I have a note about this. and this node is here. Really important thing to understand, Pyro-Solver does not create smoke. Pyro-Solver only decides how existing values change over time. Values, for example, density values, temperature values, velocity values, really important, velocity values. And when we will create our smoke, we will see how velocity values work. Just remember this line, the Pyro-Solver does not create smoke. It only calculates how the volume attributes like density, temperature, and velocity evolve over time. And I have this. So let's turn on this. You see, we are having we see nothing. We see nothing. When we connect to the Pyro-Solver, we see nothing. And here, really important thing. First connect, I will tell you, connect the test geometry density attribute into the Pyro-Solver, and you would see Pyro-Solver has source, field, shape. We also have voxel size. So voxel size is the size of this simulation voxels. So if you decrease the voxel size from here, this Pyro-Solver will have the voxel size from this parameter. What do I mean by that? You have a sphere, and this sphere inside it is made up of voxels, because we are creating a VDP. We are creating volumetric database. Volumetric database is based on voxels. So we have these voxels. These voxels are filling the sphere, right? And we are seeing the fog because these voxels have density values, right? Okay. And when you simulate this, so these density values would move into different voxels, and those voxel size will be dependent on this voxel size. You can have the same voxel size of your geometry and of your simulation data. And how you can do that? You can just put the same values, or you can reference the voxel voxel size parameter here. And what you need to do, just hit this and copy parameter, and go to your VDB, and here paste relative reference. You would see something like this. So now when you change the voxel size from here, this voxel size automatically read the values from this, and you would see the same values. You see this expression? This means read Pyro-Solver for division size, and division size here is the voxel size. No need to worry about this right now. You just this is just like to understand how this voxel size and this voxel size can be made similar. Really important thing here. Just toggle this on and press play. You'll see what is happening here. In the last video, when we talked about sourcing, and we talked about that sourcing works on each frame, works every frame. That means this Pyro-Solver is sourcing our data every frame, on every frame, at every frame. And this Pyro-Solver, what is this Pyro-Solver? First, Houdini created this Pyro-Solver to make the work easy for us. They are like very talented people, and they created some pre-built nodes. Pre-builds are for us, they created manually. And you see allow editing of contents. You go inside, you see this huge web of nodes. You see they are SOP nodes. They all are SOP nodes, and they created some objects. They created these nodes. We don't need to understand these, because if you want to do something manual later, when you become familiar with each of these nodes, then you can understand this web, and then you can modify this web, because you need to understand this web first to modify it. And here you see we have a .NET. In the last video we worked with .NET and we created our first simulation. We needed what we did, we created a smoke object, then we created a smoke solver like solver defines how these values will modify and change over time. So we also have this document, but we also have these, and these created by more talented people. Like, they are more talented than me, of course, and they created this network. And this is for like to have the similar effects as smoke and as fire. So if we want to have the similar effect manually, then we need to create these type of web to have the similar effect. So they created it, and they like promoted some parameters on the where here they promoted these parameters shape. These are, we have our forces, we have our fields, and we have our sources. But here inside you would see, now we are in the dynamic operators, and you would see we have our smoke object sparse that we created in the last video. This is acting as the object, and we have static object, static solver, and we also have the Pyro-Solver, and we have this SOP solver and source collision. These are like some nodes that we haven't talked about yet, so we need no need to understand, we don't need to understand these, but we have this Pyro-Solver. So this Pyro-Solver is defining how these values would work, and you see these are being promoted, these are being promoted to these, to here. You see here, so this is a shortcut like to create those values, to create those effects for us. So when we know what Pyro-Solver is, this like tells how these values would modify or evolve over time. We have source volumes, and when we yesterday, like in the last video, when we created our object, our solver, we created first our object, then we created our Pyro-Solver, not Pyro-Solver, sparse solver. Let me where it is, we have here, right? When we created the smoke solver, we also had, wait, where it is, here, volume source. We created this, and we have this operations, right? Yesterday we were working with these operations, and operations were like the sourcing, where we are sourcing our upcoming data into the field that exists in the smoke object, and it is working the same. Pyro-Solver also have these operations. We don't need velocity, we can just delete this. We don't need flame right now, we can delete this, but we need density and temperature, and I will show you why. We have a Pyro-Solver, and you can like decrease the voxel size to, let's say, 0.05, and when you play this, what is happening? It is sourcing our input, our values from this VDB, from particles, and you are seeing, we are seeing something like this. And here you have a shape here are our forces. Shape here means our forces, and we have different types of forces: buoyancy, wind, disturbance, turbulence, shedding, flame expansion, viscosity. Let's talk about turbulence here. Let's talk about wind first. We have this wind. The wind direction is positive x-axis. Let's say I want this to positive y-axis. So the wind is going from up to down. That means we would see something like this. We see our density values are going from these voxels to these voxels, and it is dissipating. Dissipation means the density values are fading gradually, are like getting closer to zero, and that means the values closer to zero already means that density is zero. Then that's why we are seeing this. But we see only this straight density values, this straight effect. How we can add something to create some visual interest, we have this turbulence. Turbulence is really important because it creates the natural smoke light effect. When I turn this on, when I play this, you would see nothing because it is working on temperature right now, but we have a density field here. So what I can say, I can give this density. You can choose it, you can select it, or you can just type this. Now you would see something like this. So first, let's talk about what is turbulence. I have an example for you. You have a smoke. It is rising from this platform to this, from negative y-axis to positive y-axis. You see the smoke is rising. This straight flow, we call this laminar flow. No disturbance in its direction, in its movement. When you see the laminar flow is now getting disturbed, we call this transition. And this is random moving smoke, we call this turbulence. Turbulence is like when something, let's say wind is moving in this direction, and now wind is like moving like in many direction. It's chaos, it's producing now chaos. You see chaos here. The wind is like going here, here. The wind is here, we have a straight flow, but here we have this chaotic flow. We call this turbulence. At first, motion smooth, laminar flow, then it becomes unpredictable and swirly. That is turbulence. Unpredictable, chaotic, swirly motion, we call this turbulence. And I have 3 points here. Add small scalar velocity changes. Turbulence adds some velocity changes in like any random direction. But something like this and this, not here and here. So you are creating some randomness in the smoke direction. That what is doing, small scalar velocity changes disturbs the velocity field, indirectly affects density and temperature by moving them. What do I mean by this? Disturb the velocity field. We have density, we have wind. Wind is a force here. So let's say you have this voxel, the density here is static. It is not moving. It just it is like lives here. It is just here, not moving. It is in rest. When I'm saying wind is going from down to up, wind would create here. Here the velocity value is 0. Wind would create a force, and this velocity value would become non-zero, and that's how we would see this effect. We would see our fog, our density, our smoke will move in the upward direction. So wind creating velocity, wind creating force, and force creating velocity. So when I play this, you will see something like this. And we have wind speed. You can increase how much force, how much wind, how much strength the wind will have. You can see something like this. And we have really important thing here. We covered the wind. You can just give this x and y. So now this would move in the x and y direction. And you can increase the turbulence strength. Increase it more. You will see something like this. We have this disturbed velocity field, and this is our turbulence. So we are seeing something like this. Now, what is temperature do? What does temperature do? Okay, we have buoyancy. What is buoyancy? Let's say you have smoke. Smoke have different let's say temperature. This smoke is hotter than this smoke. This hotter smoke, let's say let's give a real world example. This smoke has molecules. Molecules, when you heat them, they move fast. That means they create space, and when they create space, that means density would get like lower. Density values will get lower. because density is mass, like mass and volume. So if you have you have low mass and you have large volume, that means you have a lower density, but you have compact mass, but you have less volume, then you would have more density. And here, when you heat those molecules, they will have like higher mass but lower mass, sorry, and have large volume. That's why the density is lower. And if the volumes have, if the like element has less density, that means it is lighter, and the gravity, if gravity is pulling the same thing, one element has more mass and second element has less mass, the heavier would be pushed downwards like more strongly, right? And when you say this element has lower density, that means the force pushing lower is less strong than this density field. So this density field tends to move downward faster, like stronger, but this density wants to move but slower. So this will move faster, and these like fields that exist here have like higher density. They will get slow. They will like move stronger downwards, and this lighter weight will will experience a force by these, and these force will push this element which has lower density higher. So we have buoyancy force, and this force we call it buoyancy. You see in like water, you see when helium balloons, right? Balloons helium has lower density, that means this air will exert a force, and this lower density gas will evaporates like faster. So we have this forces, we call this buoyancy. And you have ambient temperature, reference temperature. We don't need to worry about these right now. And so if we don't have temperature, we won't have buoyancy. Buoyancy directly proportional to temperature. If temperature is zero, no buoyancy force. Now we have this. This is called temperature. These values are called temperature. So why we are seeing this fog? Because Houdini is visualizing this. That's it. These are values, and Houdini is visualizing these values as fog. These are temperature values. These values are temperature, volume attribute, temperature. Okay. Now, really important thing here. We have our source, and you can go into the source. Now we are saying the source volume is temperature. This source volume, what I want to say here, what if I want to just change this name to something else, not temperature? This will work. Let's say I want to say this hot temperature, and go here, you say source volume. I want to get the values from hot, these hot values, but here in the temperature field, you can rename this like anything. You can give this any name, but you have to source. You have to source to the right target field, and that is temperature here. Here, temperature is real. Like, what do I mean by that? I mean, you can put any name, but you have to like put this temperature string has like a value. What do I say? Has a function in here, has a function, and this function, like the temperature plays a role here. This is not just a name, it has a role. And this hot is just giving us the value. I guess you understand what I'm trying to say here, right? Okay. We have this temperature, and now when I connect this here, you see nothing. What happens now? Here Houdini is visualizing those values, these values, but here these values exist as temperature, and temperature is not, cannot be visualized, right? Temperature is cannot be visualized here. So we want our density, and we want our temperature. Just toggle this on. I am templating this. you can decrease the size. Okay, and you will see something very interesting here. I have this sphere, and this sphere, uh, oops, this sphere exists here, right? You can increase or decrease the sphere size, but I want to put it somewhere on the top of this big head. You say something like this. So what do I want to tell you here? This sphere has values which are temperature values, and these same voxels values, you see, these voxels values that are exist inside this has also density values. So the voxels that are present here have two different fields. First temperature, second density. These voxels here have only density value. Temperature exists here and density exists here. But these voxels have both. So that means these voxels would also have the buoyancy force. Because temperature, that means molecules faster in physics, but here it is just, let's say, changing the velocity, giving a force, buoyancy, and this buoyancy changing the velocity, and velocity now like moving those values in higher hierarchy, or let's say higher voxels. We have this. When I turn this on, you would see what just happened. What just happened? You see, we have a shape. Shape here is our forces. Buoyancy. When I turn this buoyancy off, what would happen? Nothing would happen. Wait, let me first toggle off our wind and turbulence so we can see it better. When I play this, you would see nothing is happening because no force is applied, but we have temperature. Yes, temperature is creating buoyancy, but we have to turn on the buoyancy. You would see something like this. So what is happening here? Now these voxels getting hotter and they are pushed, but this pushing is caused by buoyancy, not wind, not anything, buoyancy. And which voxels are getting pushed? These voxels that have the density and temperature attributes both. Density and temperature field. It's better to call them field here because we are working in the dynamics here. These are dynamics. This is our shortcut, right? So what if I move this sphere somewhere else? Like I can transform this, right? We have to like template this, not this. Okay. Now, what if I want to like move this sphere? Let's translate this then. Let's say I want to put this sphere at its nose. So translate in, I guess, Z. Yes. Z positive and Y negative. Yes. Now this sphere at its nose. So these voxels that are present in this sphere would have the density and would have the temperature, will have temperature also. When I play this, you'll see these voxels are getting pushed, only these, not these, because these don't have the density, these don't have the temperature also, these voxels have both. That's why we are seeing this. What happens if I move this, let's say in the middle, and here I want to give this turbulence also and wind also, and wind in the xy direction and turbulence here, and turbulence is working on the density too. So we will see the density is getting affected by the turbulence, but I want only temperature to get affected. Temperature means buoyancy. The voxels that are getting pushed by the buoyancy will have this turbulence, will see the turbulence effect. So you see, first, wait, let me decrease the strength of buoyancy. You'll see something like this. I can increase the turbulence value here. You will see something like this. What if I turn off buoyancy? You see something like this. And turn on buoyancy, you'll see something like this. When I decrease the buoyancy strength, you will see something like this. If I move this sphere somewhere like this, somewhere like this, so it is not like in the range of those voxels, so you will see this. You will not see the effect of buoyancy here, but you will see the effect of turbulence only. And turbulence here is on temperature, and only these have temperature because it is closer to the, you can like visualize this if you want. These, you see these voxels, and these voxels are getting affected because these voxels are like in this range and it's this range also, so it has both temperature and density. That's why we are seeing this. When I say density, we will see something like this. And I want to like share you something really important thing here. You see this blue line? That means our cache is getting stored in our RAM. Cache is getting stored in our RAM. If you change the value, like change something, let's turbulence, you see our cache is turned orange. And that's why. That's because this cache has to be updated because we changed something here in this parameter. So this cache is not like workable because we changed something here. If you want to see this change, we have to like recalculate this, and this blue is now recalculation, and this cache is now stored in our RAM. When we change something here, it will wait a second, it is calculating. It will turn orange. You see, this is now outdated cache. So I think this is it for this video. We have talked about buoyancy, vent, turbulence. These are really important things if you want. We have also look. We don't need to cover it. When we cover the pyro, we will see this look tab also. So I think this is it for this video, and I hope you are doing well. And keep learning, keep practicing, keep creating, and I will see you in the next one. Until then, bye bye.